algebras, all algebras, and F1 linear categories. Thank you. So basically my goal is to discuss a set of examples of categories, which I'll call F1 linear, and maybe I'll get to explain a little bit later why I say this, or why I use this name. So these will be categories which have some sort of relatively strange properties. So these are non-additive categories. So in fact, it will be the case that given two objects, Hom may be the only structure this Hom space will have is that it's a pointed set. And the fancy name for a pointed set is an F1 vector space. So that's why I call these things F1 linear. And nevertheless, these categories have some nice properties and behave in many other ways like abelian categories. So by this I mean that all morphisms of these categories are kernels and co-kernels, and we can talk about exact sequences and complexes, and actually try to do some type of homological algebra in this sort of non-additive setting. Okay, and the other feature that these categories will have is that given such a category C, we'll be able to make sense of its Hall algebra. So this is a pointer from such categories to Hopf algebra. And this Hall algebra construction will provide a categorification of a number of combinatorial Hopf algebras that sort of pop up all over mathematics. Okay? And so examples of such category C, and I'll probably only get to one of these examples, but so Feynman graphs form such a type of category. There's representations of monoids. By a representation of a monoid, I mean a pointed sets together with an action of the monoid. Another example is something I call incidence categories. These are categories that are constructed out of a family of partially ordered sets that are entirely combinatorial, as well as categories of coherent sheaves on schemes over F1. So,
when you say nomadic, do you mean it's not required, or you don't know?
In all these examples, all these categories are non-additive. So, as I said, Homs would just be pointed sets.
So it would be okay because
No, I don't want these to be additive specifically. Okay, so the plan is to right. So actually, since there's no way I'll get to this example, maybe I should just mention that there is a notion of a scheme over F1. It's an object that's locally defined by the spectrum of a commutative monoid, and it's glued from such spectra the same way an ordinary scheme is glued from spectra of commutative rings. And the structure sheaf of such an object is a sheaf of monoids, and one can talk about coherent sheaves and so on, but it seems extremely unlikely that we get to this point. Okay, so my plan is to just first discuss what Hall algebras are, and then maybe go through some of these examples. Okay. So, what are Hall algebras? Well, Hall algebras are algebras that somehow measure the structure of X1 in a given category. So suppose we have a category where exact sequences make sense. So we can talk about short exact sequences, and we have some additional properties. We want we want the Hom space between two objects to actually be finite as a set. And we also want x1 to be finite as a set. So typical examples of categories of this form before were maybe, for instance, representations of quivers over a finite field or something like that, representations of finite dimensional algebras over FQ. But as I said, I'm interested in this sort of non-additive setting. So here really, these would just be sort of pointed sets, and I want them to be finite. And given such a category, we can try to cook up an associative algebra from it. So HC, this is the Hall algebra, and it's defined as follows. So first I'll give a sort of very explicit definition and then a more invariant one, which is, so I'm going to use the square brackets to denote the isomorphism class of an object. And then we can try to multiply isomorphism classes as follows, by essentially summing over all short exact sequences which have A and B on the ends. So I have to mod out by some symmetry factors here. And this number here is the number of short exact sequences of the form. So I'm assuming there's some sort of zero object in these categories. So we just sum over all possible ways, all possible isomorphism classes that extend A and B. Okay. So this is clearly an algebra that encodes the structure of x1, and the statement is that provided some very weak conditions hold that I don't really want to get into now, this will be an associative algebra. So maybe a better way of thinking about the whole algebra, a more invariant way, is that it's a set of functions on isomorphism classes in our category. So here I want to identify this square bracket A with the delta function supported on the isomorphism class of A, and then given two such functions, if I want to evaluate it on an isomorphism class, then what I do is I sum over all sub-objects C of A and perform this type of convolution. Sorry, my notation here is not consistent with the previous notation, but hopefully you get the idea. So it's a space of functions on isomorphism classes, and from this perspective, there's something we can try to do, which is we can also equip it with the coproduct, where we send a function. The coproduct of a function evaluated on a pair of isomorphism classes is f evaluated on the direct sum. Okay. And the statement is that in all the examples that I would discuss, these two things will be compatible. And in fact, the whole algebra will become a co-commutative Hopf algebra, and as such, by the Miller-Moore theorem, it's simply the enveloping algebra of some Lie algebra, which we call the Hall Lie algebra of the category C. Okay, so let me give an example of one of these categories that I have in mind here, which is Feynman graphs. So I'm going to take the example of Feynman's theory in physics. So this just means that look at trivalent graphs. So for our purposes, that's all phi cubed means. So examples of such things are okay. So these are the types of graphs we're interested in, and so objects of this category are exactly these trivalent graphs. And a graph to me doesn't have to be connected, so it can have an arbitrary number of components. And I'm going to define morphisms in this category as follows. So given two graphs, gamma 1 and gamma 2, morphisms are given by triples of the following form. So here, little gamma I is a subgraph of big gamma I with 2 or 3 external legs. Okay. The reason this condition is imposed is because I want the category. Oh, let me finish the definition and then I'll explain more. And F is an isomorphism from gamma 1 mod little gamma 1. So by this I mean the graph that's obtained by collapsing each component of little gamma 1 to a point. So we shrink every component of little gamma 1 to a point, obtaining another graph, and we insist that F be an isomorphism from that resulting graph to little gamma 2. So all we're doing here is we're specifying effectively the kernel of the map, which is little gamma 1, that's the thing that gets killed, and the image of the morphism. Okay. So let me just give you an example of how this works.
And if little gamma 2 has automorphisms, you keep track of that as well?
Well, that's why I specify little f. I have to pick an isomorphism, and in general there will be several.
Do these graphs have any kind of ribbon-like structure, or there is
no? Well, for me they are.
Graphs.
I mean, you can probably. This is very generic. I'm sure you could do this with ribbon graphs also, and so on. But my graphs are just plain graphs. So here's an example of a morphism in this category. So here's my gamma 1. Okay. Here's my gamma 2, and I'm going to give you a map from one to the other. So I need to specify this triple of things, the gamma 1, gamma 2, and little f. My little gamma 1 is going to be this guy, and my little gamma 2 is going to be this guy. So let's see that this makes sense. If I take little gamma 1 and I shrink it to a point, so I just forget that there was ever a graph here and replace it by a line, then I'll get this thing. Okay? And that's exactly the same thing as this graph here is isomorphic to little gamma 2. And what I need to do is I need to specify some type of isomorphism. And you can see that there are two isomorphisms that are going to work. So, for instance, we can specify it as follows. All right, so as I said, now perhaps you can see why I insist on this condition that the subgraphs have 2 or 3 external legs, because when I collapse the graphs, I need to stay in the category of trivalent graphs. If I start collapsing other graphs, I'll get vertices that are no longer consistent. So the claim is that this is a nice category. It has kernels and co-kernels. We can talk about exact sequences and complexes. Disjoint union gives us a symmetric monoidal structure, and we can talk about its Hall algebra. And so the Hall algebra of this category is something called the Kohn-Primer algebra. precise, it's actually dual to what people typically call the primary Hopf algebra. And this Hopf algebra that came out in the sort of mathematical study of renormalization because it encodes the combinatorics of the BPHC algorithm when you renormalize. So, roughly speaking, when you try to calculate the Feynman integrals that come up to these graphs, they diverge, and what you need to do is you need to add and subtract various contributions coming from subgraphs so as to obtain a finite answer. That there's a combinatorial algorithm for this called the BPHC algorithm. And I guess it was like Kreiberg's insight originally that this combinatorics reflected the existence of a Hopf algebra structure here. Okay. I probably don't have a whole lot more time, but so there are many examples of such categories. So you can see obviously here that there's no easy way to kind of add morphisms. But for instance, you can look at quiver representations over F1. So you can consider representations of the quiver basically in the category of pointed sets. This will again give you a category which has a lot of very similar flavor to it, and which has some sort of degenerate behavior corresponding. Which if you compare this category with the category representations of the quiver over FQ over a finite field, then this thing sort of gives you a sort of very degenerate behavior at Q equals 1. It's not exactly just setting Q equals to 1, but it's some sort of very degenerate version of it. And you can sort of cook up many categories with this flavor. And so, they really sort of do have the kind of feel of an abelian category, but they're not additive. And there's some sort of natural problems in this context to try to make sense out of some homological algebra in this setting. So, for instance, we can talk about X in these categories. So. And many other notions. You can define X via the Uneta construction. What's much less clear is that this can actually be computed in terms of anything like a resolution and so on. Let me just finally mention that there's a recent preprint of Dietmar, who's worked on sort of schemes over F1 and so on, and he calls these types of categories Boolean categories. So not abelian, but just Boolean. And he has developed some sort of homological algebra in this context. And hopefully that'll lead to something interesting. Okay, thank you.
Questions? Would it make sense? What would happen if you fixed some ground field and you took the vector space spanned by isomorphism classes of these things? Would that give you, if say you did some vector space over SP, would that give you? That would also presumably give you some kind of category with finite homes. You
just want to sort of take the linearization of this and take the span. Okay. If you just do it like that, then you'll lose the properties as all maps of kernels and co-kernels. So all these categories do come with sort of a base change to abelian categories. What you would do in this case is there's a forgetful functor from all such categories to pointed sets. Once you hit pointed sets, you can just take the span. There you can take the span, but sort of directly here it wouldn't really work. So yeah, that's why I call them F1 linear, because these categories are enriched over pointed sets or F1 vector spaces, and so it's they all sort of come with a base change to a field, but not in the most naive way.
Is there a physical reason that you want to be finding that in terms of geometry over F1?
Well, nothing beyond speculation. So I should have mentioned also that typically you can even define the algebraic K-theory of these categories and things like that, and what one could hope or speculate that those K groups, one expects to have some sort of almost homotopy theoretic interpretation. For instance, if you take the algebraic K-theory of just F1 vector spaces, it turns out that those are the stable homotopy groups of spheres, and so on. So if you take the algebraic K-theory Feynman graphs, you can ask, what's the concept of that? And I don't know, but maybe it has something to do with the sort of arithmetic nature of the periods you get when you evaluate these integrals or something. But I mean, that's just a pipe dream. I don't really know.
What is the final Lie algebra? Sorry, the whole Lie algebra.
Oh, right. So yeah, I should have said so. So that if given two graphs, the Lie bracket has this form. So this operation, this triangle operation, is all ways of inserting the graph gamma 1 into gamma 2. So you can open out a vertex and glue in a graph, and this is all ways of doing that.